All right. I think this should work now. I'm not sure though. Let's see. Does this work? Open folders. All right. So, what are we going to do today? We are live and we are vibing. No, of course not. So, I have seen Jon Gjengset doing the 1 billion row challenge, which was kind of a pretty hyped thing by a bunch of influencers back in the day. And like that, what they did is basically someone put out a challenge of parsing 1 billion rows. Probably all of you have heard of it. They contain city names and temperatures. We have to report the min, max, and average temperature. Yeah, basically the challenge is that you have to parse 1 billion rows as fast as possible. And today we're trying to lay the ground bricks to actually accomplish a quite acceptable time. Let's first look at the 1 billion row challenge again and view the rules. I will share rules. Let's make sure everything's working fine. Yeah, rules and limits. We have to, of course, we're not gonna use Java. We are not gonna use Rust. We are gonna use Bear C. Yeah, no external libraries. We're not gonna do that. Implementation must be provided as a single source file. Okay. Station name non-null UTF-8 string of min length 1 character and max length 100 bytes containing neither a semicolon or a new line character. A temperature, a non-null double between negative 99.9 and 99.9, always with one fractional digit. There's a maximum of 10,000 unique station names. Line endings in the file are a line feed. Characters on all platforms. Implementations must only rely on specifics of a given dataset. Must not rely on specifics of a given dataset. Example given any valid station name as per the constraint above, and any data distribution must be supported. Number of measurements per station. Right. The rounding of output values must be done using the semantics of IEEE 754 rounding direction round toward positive. Okay. So basically what we have is a gigantic CSV file. I have already generated it, so we start with a clean slate where we have the measurements. Yeah, it's gonna take a while to load it up. Let's see. Oh man. Is NeoVim doing this? So VS Code, I don't know if it does it, but I mean theoretically it just has to show the first couple of lines. I don't know if it can do it. Can it do it? Oh, there we go. So as you can see, we have a bunch of lines here. I hope you can read this. It's a little bit shitty, I know. Also the font is probably not the best. So each line has a city name. It's actually pretty simple. And a measurement. So 0.5 is a temperature. 27.3, 6.4, 6.7, and so on. So let's quit. I also ran the baseline in their repository, which gives us a basically a map that tells us the min, the max, and the average. So this is probably min and average and max. Yeah. So do we have Berlin in here? Berlin, we have negative 42.4, which is not very realistic, but okay. 10.3 and 61.0 as the max. Now, of course, each city appears multiple times in the measurements.txt, and we have to aggregate all of the stuff that's in the measurements.txt. So we're gonna do it in one C file, and we are gonna call it 1brc. 1brc.c, and it gets a main function. Of course, we return 0. We also maybe want a build script. We want a build script, which I don't know if we should. We're probably using Clang. So the machine I'm using is a pretty old machine. Let's see. So how do I show you this machine? So it's pretty old. It has a pretty fresh Arch Linux install, but aside from that, nothing new. So it has tmux lcpu. Let's see. Also, all of these things are not working. So you can see I have a Ryzen 5 2600, which has 6 cores and 12 threads. It has a clock rate of 3.4 gigahertz. Of course, AVX2, stuff like that is supported. We have an L1 data cache of 192 kilobytes. So that's for let's see, Ryzen. I think this is for also 1/6. So it's 32K of L1 data cache, and the instruction cache appears to be a little bit larger. So that's 64K of instruction cache, 3 megabytes of L2 cache, and 16 megabytes. Oh no, 3 megabytes. So 3 divided by 6. Oh my goodness. You can do that in the head. So that's half a megabyte of L2, because every core has 1. And 2 times L3 cache. I don't know if that's actually true. Ryzen 5 2600. Tech power up. Let's see. So where does it? Oh, it's 90. Huh? I don't know, maybe this is completely nonsense what's here. So tech power up says 96k of L1 per core. So that's much more than 192. Oh yeah, it's, oh no. Okay, I think this matches. Like, we have 96 times 6, so that's 576k, and 192 plus 384, that's also 576. Okay, so that is accurate. So L2, yeah, half a megabyte, and yeah, whatever. We shouldn't waste our time on this. Yeah, that's the system we're working on. We have 16 gigabytes of RAM. I don't really know how you do that on Linux. How you can ls memory Linux. No. CPU for memory. I don't know. There's probably something you can do, like get memory initialized Linux. Varlog proc meminfo. Yeah, whatever. Yeah, let's just not bother with that. So let's start with the basic C function. We wanted a build script. We're using Clang version 21, I guess. Yeah, 21.16. Clang-g-o 1brc and 1brc.c. We're using a single file, which is okay, and our code will only work on Linux. So we don't bother with platform-specific and platform-agnostic code and separating it. We're just gonna dump it all in one file. Oh man, this font looks so weird, but okay. I don't really like this font, but okay, let's not bother with it. Let's include some types, standard int, and let's type def our integer values so that the Rust guys are not complaining. So we also have this in C. I think they use i8 and i16, 32T, i32, and 64T, i64. Then we also can type def the float as an f32 and the double as an f64. Okay, we may not need all these, but now we just have them. Let's also pound define KB as 1024 times x. Let's also pound define MB as 1024 times KB of x. And let's also pound define gigabytes as 1024 times megabytes. All right. So we have some basic stuff here. Now, our file name is, yeah. So first of all, we should probably start and conceptually speak about how we want to do this. I mean, in the end, we want to use all of the parallelism we got. We got 6 cores and 12 threads. So each core can have 2 distinct instruction streams. Let's see how that actually works out. But we want to design our program in a way so that we can parallelize it easily. So I will have a pound define as a constant, and I call that lane count. And let's set lane count to 1, and lane count is the number of threads we are going to use. All right. So first and foremost, we probably want to open the file. Let's not discuss how we do this. So we look at man open to see how we can open files on Linux. We need to include fcntl.h, and I don't actually know what that stands for, but whatever. We open measurements.txt, we just hard code it and don't care, and we open it with ORD only because we only want to read the file. So we also don't perform a check, whatever, it's just there. So normally you would do something like if fd is -1, return 1 or so. We don't care about that for now. Yeah. We probably also want to get the file size. The file size can be retrieved using something like stat. Here we go. We need to include sysstat, which is just syscall into the Linux kernel. And then we can also, let's extract this, car star file name is equal measurements.txt. File name. We could also use fstat. So the final result is gonna be stored in the stat buff. This is our file stat, so struct stat, and we're gonna use fstat, and fstat operates on the file descriptor and not the file name. We can use fd here and pass in a reference to file stat, and this is gonna return either 0 or -1, but we don't check for the result. It shouldn't fail. So usually you should do that, but let's don't care about that. If it fails, whatever. So let's get the file size. Let's look at man struct stat. Struct stat. Let's look at how the stat struct stat man stat. Oh, I don't have man installed here. Okay, that's bad. Man stat 3 file status, no. 4 stat 1, no. Stat where is it again? So stat 1 struct stat. We don't want to waste time on this. Where do we see the fields? Okay, let's do something different. Oh. Let's user include envem user include, and we have sys stat. Here we go. Struct stat. Where is it? Where is it? Struct stat. Is it not defined in here? Oh, that's bits types. Okay, I think maybe it's in types. Ex bits types types.h struct. Nope, it's not in here. Where is it? Where is it? Sys. No, not syscall. Sys stat. Here. Features. Bits stat. That has to be it, right? We're wasting. I mean, it's kind of a waste of time here, but what was it? I forgot what it was. Shit. Bits types. No. Bits stat. Bits stat.h. Bits stat.h. Struct stat. Oh my goodness, it has another header. Nice. Struct stat. Struct stat. Oh my god. Okay, as you can see, if not def, okay, we have a padding. We have an st size in here. St size, which is the size of file in bytes. All right, this is what we want. And this is an off t. I don't know what an off t is. Yeah. Let's just say it's 64 bits. So this is our file size, and this is filestat.st size. Great. Now, most implementations probably use something like a memory mapped file in Linux. Memory mapped files basically allow you as a user just to refer to the file with a pointer, and all of the magic is going on in the kernel. There's a sort of file reading and all the caching stuff. Yeah, let's just do that because it's the most easiest way of doing it. We may explore some other stuff as well. Yeah, it's probably faster than just using a read syscall, and yeah, let's just see. So mmap takes an address if you want to map to a specific address, but we don't want that. We just want some address. So let's see, void, we get an address, and we know how large this is. It is file size large. It also needs some protection flags. It's also explained here. We have prot read, prot write, prot none. We want prot read. We also only read from this. We want some flags. So we maybe want to look into huge page mappings, but let's just not consider this for now. Let's just use map shared, and you could probably also use map private. It probably doesn't matter. Then it takes a file descriptor, which is obviously our FD, and an offset into the file, and that is 0 because we want to start at the very beginning. So now we have an address, and this address will contain the actual first will contain the bytes of the file. So if we, for instance, say, okay, printf, we also need to include standard IO for this. If we printf adder percent dot star s, I think it's like that, and then we say print the first 10 bytes and cast this to U8. I think maybe void star also works. Let's see, let's close this and let's actually build this. Permissions denied, chmod plus x build. Okay, format specifies type char star. Yeah, we probably have to. Yeah, so this builds. So now we have an executable, one BRC. And as you can see, yeah, maybe you can't see it. Let's also just add a new line here. As you can see, these are the first 10 bytes of the file. And if we do something like head -n1 measurements.txt, yeah, you can actually see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 up to the 0. These are the first 10 bytes. I think, can you also specify bytes? Yeah, head -c 10. Yeah, there you have it. It's the same thing. All right. So we can read the file. This is pretty good. Normally we would have to use something like read and then use the file descriptor and then put in a buffer. We have to allocate a buffer for this, and so on. So this is pretty neat that we can do that, and all of the hard stuff is going on in the kernel. And it's probably gonna take care of it good or wisely. If not, we have to do something else. But let's just do it like this for now. 1 second. Let's actually see. All right. Let's go back to the scene. Yeah, so we have this address mapped. We probably want to unmap it, but I mean, if the process is killed, it will get unmapped automatically by the kernel. So we don't really have to do that. If you want, you can. You probably should. I don't know. Consult a professional if it is in question. Yeah. So later we maybe want to map huge tables. What huge tables are is basically so the CPU has something like a TLB, a translation look aside buffer, because we have virtual and physical memory. And the operating system actually has to fill in these tables. Now, if we use a page size, and obviously the physical addresses, it kind of, yeah. So we have virtual and physical memory, and the OS takes care of the mapping. Now, if we have not mapped a physical address to a virtual one, the CPU will complain. And the CPU will call the OS and say, hey OS, please map the virtual memory to the physical memory, and we're gonna be good to go. Now, if we use a page size that is pretty small, and let's say standard page sizes on x64 are 4K, and if we have a file, I mean our file is pretty large. Let's actually print our file size. File size. This will be in bytes. We can also do lsllh dot, and then we see that this file is 13 gigabytes. So 13 gigabytes and divided by 1024 times 1024 times 1024 divided by 4 divided by, oh not mod, divided by 1024. So this is a lot of pages. And each time we hit a new page, the OS has to go, the CPU is gonna wake up the OS, the kernel, and the kernel has to map in the address space. Now, if we use larger page sizes like 2 megabytes, we have far less pages and far less page faults. So if the CPU tries to access memory that's not mapped, it will issue a page fault. That's actually what it's called. It's a page fault. And when we increase the page size, we effectively lower the amount of page faults. Maybe we want to look into this, but for now we're not gonna do this because I probably have to set some settings in, because out of the box, I think you have to override something in the boot settings to have a huge table, huge pages, and yeah. So forget all of this. Basically, remember, okay, we might want to increase the page size to 2 megabytes because then we have less page faults. The OS is getting waken up far less, and we're not gonna pay that much of a performance penalty, but that's for the future. So we are having this address. Now, what we want to do in the future is we basically want to construct this code in a way so that we can easily increase the thread count. Now, one way to do this is basically say, okay, we have an entry point for all of our threads. And let's just call it entry point. And entry point is a void star and also gets a void star. Why is that the case? We can see that. P thread create is the syscall is the syscall we want, and p thread create takes a start routine which is of type void star and also takes a void star. Here, type of void star takes void star. So the function signature has to be this. We could also do something like type def thread routine. Can we do that? Type def void star thread routine void star, and then say this is of type thread routine, or so. Was it? Yeah, no, you could do something like thread routine test, right? Is that true? I forget. No, you can't. Oh yeah, okay, no. This is not how it works. This is not how it works. We don't define, forget what I did. Void star entry point void star args. All right. This is exactly the function signature. And what we're gonna do now is we want to spawn a bunch of threads. Exactly, and how many threads? Well, that's defined in lane count. Now, to do that, we just call pthread create. Pthread create takes some pthread restrict thread. So this is kind of the thread metadata. I mean, we can look at this. Let's first include pthread. I don't know if VS Code has an easy way to do this. User include pthread. Struct pthread t. Pthread t. Where's pthread t coming from? We don't know where it's coming from. We don't know the definition. Pthread t. Oh man. Yeah, whatever. We're not gonna inspect the type now. Yeah. So to store this thread handle, it's basically a handle to the thread. To store this thread handle, we can have an array of these handles. T handles, and this is of size lane count. Now we pass in handles. Now I said we want to do this for each, we want to do this lane count times, so we have to actually use a loop. Let's define a lane IDX, and while the lane IDX less than the lane count, lane IDX plus plus, like that, and we create a thread with a reference to handles at lane IDX. Then the next thing is a pthread attribute t. Now pthread attribute t we don't care about, we just pass in a null. Then the start routine, which we defined as entry point, and also arg. So let's say, okay, arg. No, don't say arg is null. Let's say, so for typically each thread wants to know which kind of number or identifier it has, so that we can assign the work pretty neatly. How are we going to do this? We define a struct, and we call this thread context, and struct thread context, and the thread context for now just has a lane index. What we're now going to do is we also have an array of thread contexts. Thread context contexts. This is cursed. And we could say something like pthread t thread t handle is equal to handles at lane IDX, and obviously the thread context star contexts at lane IDX. Now here we also want to set context lane IDX to the lane IDX. And this last attribute here, or this last parameter of the function, is just a void star pointer. This can be anything. This is just a pointer, and this is gonna be the thing that's passed into our entry point. So here we can now say thread context is equal to args. So this is just a pointer cast, and we can say u32 lane IDX is equal to context lane IDX. This is how we are parsing. This is how we are passing arguments to the thread. Now, this should already kind of work. Of course, this function here should also return something, a void star. We can just say null. And what we also have to do is we have to sort of join the threads. So let's look at documentation for pthread join. So pthread join waits for the thread specified by thread to terminate. Why do I have to do this? So if we don't call join, all threads will just be created and we return 0, the process gets killed while these are still running. We don't want to terminate the threads early, we want to wait for them all to return. So what we are going to do is we are going to create a new loop after creating all of the threads. We are gonna join them together. So pthread join on handles at lane index, and we also have a red val. So this is the return null. At the moment we don't really care about this. Maybe we want something returned here. Maybe. So let's pass it in there. Pthread join, and that's it. Yeah, so at the moment we're not really doing anything in the threads. So let's just say we printf the lane index. Unsigned lane index. Hey there, I am thread this. Let's build 1brc. Hey there, I'm thread 0. Let's actually quickly remove this, and if we increase the lane count and build this, we're getting a bunch of threads. Now, if we don't join, this is what I was trying to explain to you. If we don't join, we're just getting 2 threads. We're canceling early. This we want to avoid. We want to wait for all the threads to finish. And yeah. So let's actually remove this print. We are now in the situation where we can spawn a bunch of threads. Now let's reduce this to 1 again. Let's reduce this to 1 again. Yeah, so each thread now has to know which kind of chunk. So what is the idea? What is the idea? Let's get the drawing pad. We have a gigantic chunk of work to do. So this is our measurements blah blah blah.txt, right? And now we have lane count threads, which means we want to split this entire file into chunks, into lane count chunks that are almost equal size, so that each thread almost has the exact same amount of work to do. So this is for 5, lane count is equal to 5. Now, obviously the chunks won't really be that nice. I mean, we have the first problem is that probably the chunk end won't be a new line, and the chunk beginning probably won't be the start of a line. And we also have the problem that this last chunk, if we just do a simple divide of the file size by the lane count, the last chunk is too small. So how do we do this? It's actually pretty simple. So first and foremost, all of the threads have to access this stuff. So basically, yeah, probably people are not gonna like this, but I don't care. We're just gonna do some global variables here. We have a static u64, a static void star address. We have a static u64 file size. We have a static u64 chunk size, and these are going to be filled in on the main thread. So we can say here file size is this, chunk size is equal to file size over the lane count. So this will do a divide, but it will floor. So for example, if our file is 13 gigs large and we have 5 of the chunks, 13 divided by 5, each chunk will be too wide, and therefore the last, yeah, this is probably not the greatest way of doing it, right? We could further split this. Okay, now 13. So we see yeah, how do we do this? So 13 gigabytes divided by 5. So that's that. And 5 times, was that actually, did that work out? So 13 times 1024, 1024, 1024 divided by 5. This is not a floating point value, right? Oh man. Times 5 is that again, okay. Whatever. We just say the hangover in term, if it doesn't work out, is just assigned to the last thread. Is that the best way of doing it? I don't know. But whatever. So, how does each thread know? How does each thread know what to work on? Now it's pretty simple. We know the chunk size because it's a global variable. Each thread has access to it. And we know the lane index. So this is the thread index. This is why we passed it to the thread. So by simply multiplying the lane index into the chunk size, we get the start. Chunk start. And we can also get the chunk end, which is equal to the chunk start plus the chunk end. Now we have one critical limitation. That is, if the file size minus the chunk end is less than the chunk size, so if this last if the hangover is less than the chunk size, which is only true, like this should only be true for the last thread. Like let's put it here. This should be only true for the last thread, but let's just let them execute it all in parallel. I don't care. Then we want to set the chunk end to file size. Now then we can retrieve the chunk, the actual chunk size, or yeah, actual chunk size is equal to chunk end minus chunk start. All right. So let's, for each thread, just print the actual chunk size. Yeah. Thread and percent unsigned. And this is the size it got assigned. So lane index and actual chunk size. It doesn't like that. It wants LU. Okay, now we have just one thread. If we increase the number of threads to say 4. Yeah, this, you can see this is not correct. Chunk start plus chunk end. This is chunk size. Oh man. Yeah, as you can see, one thread now has 2 bytes more. You could further split this, but I mean, in the end, you can just have a maximum hangover of 3 if you have a lane count of 4. Because you can only have a max remainder of 3. And I think we don't really care about this. Like here's perfectly matching. Here 2 bytes. Like, okay, let's actually put the numbers together. 2 7 5 9 0 6 2 3 1 6 times 4 times 5 plus 2. And is this correct? ls la. Yeah, this seems correct. All right. So each thread now knows what to work on. Now this didn't fix any of the problems. I mentioned before that because only the first thread really is guaranteed to start on the start of a line. So we have to do some work here to actually get that. But for now, let's just don't consider it and move on. So let's just do some basic stuff on this file. Let's have a counter for each thread. Let's just have a counter for each thread. This we can achieve with Clang with the __ thread built in. So this will just create, this will basically do this. It will do static a U64 counter, a lane count, and then it will index. I don't know if it actually does that, but it's basically the equivalent. So, but this is a little bit nicer to write. So let's just iterate over the entire size. I is less than actual chunk size. I++, and let's just let's have a pointer, a U8 star, chunk adder is equal to adder plus, so we also have to cast this to a U8, I guess. Adder plus the chunk start. And then we're going to just do a basic sum over all of the bytes. And each thread will now print its thread ID, and its count. So lane, IDX, and counter. And let's see if this works. It's segmentation faulted. Now that's bad. Why did it do that? Lane count, let's reduce it to 1 for now. It also seg faulted. Did we store the address? Oh no, we didn't. We didn't store the address globally. We just created a new variable and didn't store it in the global variable. This is obviously very stupid. And as you can see, this now works. It's taking quite some time. Let's see how long it takes. Oh my gosh. Why does it take this long? I wonder. It shouldn't take this long. Let's increase the lane count. See if it still takes as long. Okay, now you see it was a little bit faster. Just a little bit. Oh yeah, we built. And we can probably already see, I mean, we are compiling with debug symbols enabled and no optimization. Let's do a time on this. Let's just quickly see how long it takes. Oh man, it's pretty slow. It is pretty slow. So summing the bytes takes 32 seconds. This is not a good measurement. If we use 03, now we would actually have to make sure that this is actually, I mean, it has to sum it, right? It's the same result. Yeah. It comes down to 2.314 seconds. So 16x improvement just by changing 2 letters here. That's pretty wild. We're not looking at the assembly here, but what we should be doing. Yeah. So they're probably doing some heavy, aggressive optimizations here. We could actually look into this. I wonder. Can we just show? Can we? This wants to use GCC. I don't know, man. I don't know. Okay. I don't know. I have to figure out this debugger setup. What if we paste? Let's just pay. I mean, it's a single file. That's pretty nice. Let's go into godbolt.org. C clang clang 21 x8664. Let's remove this. Let's paste it in here. Okay, let's look at this. Okay, so a bunch of stuff. Let's just filter out the main. I don't think it does anything on the main. Okay, whatever. Let's look at entry point. So we have a bunch of stack stuff. Blah blah blah. So where's the loop? Here. Here you see we have a mov. This is pretty nice. Quad word pointer fs0. So an LEA counter at TP off. Okay, so this is a hard-coded address. This is the hard-coded address of the thread counter, which lives somewhere. So we move fs0. What the heck is fs? Yeah, we move into RAX and then we add RAX plus RAX into RAX. So RAX plus the counter into RAX, and then we add RCX. We add RAX. No. LEA. This is the add. What does it do here? Counter TP off. Control left click. So the counter lives here. Good. So where does it write back into the counter? Counter plus equals load effective address. Oh, RAX is no. RAX counter plus RAX. RCX. What? Okay, let's turn on optimizations. Let's just see what it does. See it unroll. It unrolls the loop a bunch of times. Oh man. I thought this would be a lot simpler. Why is it generating this code? Who knows? This seems overtly complex. Just for... This is a lot of code. Whatever. This seems like a little bit too much. I mean, this is just a basic loop. Like, you have a counter. I don't even see where it stores it. Where does it store it? So where does it call printf? Here it calls printf. LEA-RX plus counter TP-off. Interesting. Mov RBP minus 64. Is this? Oh, and as you can see, you also have like all of our strings. They're obviously also compiled into this. Yeah. Whatever. What we're probably now interested in is in collecting some statistics on our code. Now Linux has perf. I actually didn't. So perf to man. Perf to man. I don't want to use the perf command line tool. I want to use something else. Can we install perf? I mean, we should have perf, like perf header Linux. Perf. No, this is not what I want to use. Using perf on Linux, util perf event open, like this is what we need. Okay, there's a bunch of stuff. So modern CPUs, especially x64 CPUs, have a bunch of performance counters, like cycle counts, TLB, misses, branch mispredictions, stuff like this. And using perf, we can get pretty easy access to it, I guess. Now, okay, we need all of this stuff. We need, let's include this. Syscall Linux perf event Linux hardware breakpoint. Okay. Perf event open returns a file descriptor for use in subsequent system calls. A call to perf event open creates a file descriptor that allows measuring performance information. Each file descriptor corresponds to one event that is measured. These can be grouped together to measure multiple events simultaneously. Events can be enabled and disabled in two ways, via ioctl and proctl. Probably we want to do this per thread, but I don't know if we want to. So let's just do it per thread and see if it actually works. So we have to make a syscall. Let's just try and do it at the very beginning of entry point. Syscall. Sys perf, stuff like this, right? Sys perf event open. Then we need struct perf event attr. Struct perf event attr. Perf attr. I don't know what it has. So it needs a process ID in CPU group of D. I never did anything with this, so we have to see how it works. So process ID. Let's see. Can you use it for multiple threads? Can you use it for multiple threads? Can you? All right. Okay, so arguments, PID and process ID and CPU. Process ID 0 and CPU -1. This measures the calling process thread on any CPU. This is what we want. Okay, so perf attr. I think this is a pointer, yes. And 0, -1. So group of D. Group of D argument allows event groups to be created. An event group has one event, which is the group leader. The leader is created first with group of D -1. The rest of the group members are created with subsequent perf event open calls, with group of D being set to the file descriptor of the group leader. A single event on its own is created with group of D -1 as is considered to be a group with only one member. An event group is scheduled onto the CPU as a unit. It will be put onto the CPU only if all the events in the group can be put onto... What? I don't really know what this means. Let's just set it to 0. Why groups? Probably that's a very good reason. And we also have flags. So this flag enables a close on exec flag for the created event file descriptor so that the file descriptor is automatically closed on exec v. Okay. Per flag fd no group. This flag tells the event to ignore the group fd parameter except for the purpose of setting up output redirection using the per flag fd output. Maybe we need no group. I don't know. So I don't know if we need this. Let's see. Pit C group. I don't know. FD output. This flag reroutes the event sampled output to instead be included in the mmap buffer of this event specified by group of D. Okay. Perf event attr. So this is what we want. Type of event. What the heck? Size of attribute structure. Type of specific configuration. Yeah. Type. Perf type hardware. This indicates one of the generalized hardware events provided by the kernel. See the config field definition for more details. Perf type software. This indicates one of the software defined events provided by the kernel. Okay. Perf type trace point. This indicates a hardware cache event. Dynamic PMU. Perf event open can support multiple PMUs, performance monitor units. To enable this, a value exported by the kernel can be used in the type field to indicate which PMU to use. The value to use can be found in the sysfs file system. Config. If type is perf hardware, like let's say perf attr dot type perf type hardware. All right. We are measuring one of the generalized hardware CPU events. Not all of these are available on all platforms. Set config to one of the following. Perf count hardware CPU cycles. Cycle count is set config to one of the following. Retired instructions. Count hardware cache references. So do we need a perf event open for all of these? Software page faults. Like these, we should. Oh, this is probably why you do a group FD, right? So one of these instruction, let's just try and do one. Let's just get the CPU count, the RDTSC. I don't know if it uses RDTSC under the hood for count hardware instructions or CPU cycles. Let's just try and do that. Perf attr dot config perf count hardware CPU cycles. Now on x64 there is an RDTSC read timestamp counter, which is an approximate cycle counter. I don't know if it actually uses that because there are other ones as well. PMU on Zen 2. Yeah, it also has the performance monitoring counters. I don't know which ones. We could look at the documentation, but whatever. So, perf count hardware CPU cycles. Okay, how do we actually, what do we do with this? Like this is an int, I don't know. Look at how much stuff we have this here. Perf count hardware cache L1D. Data TLB. Instruction TLB. Branch prediction unit. Read access, write, we can do so much stuff. I don't know if we can do it on the CPU, but yeah, I don't know what we have to set for a minimal setup. What do we have to set for a kind of minimal setup? That's the question. Let's ask Gemini. Let's ask Gemini. Okay, Gemini has something here. I don't know if this is correct. So it has. Okay, we need perf attr dot size size of struct perf event attr. I don't know if we need that. Perf attr disabled 1. Okay, this seems counterintuitive. Perf attr dot exclude kernel 1. This is reasonable. We don't want the kernel cycles. Exclude HV hypervisor. We don't have a hypervisor. Okay, we open the event. Reset and enable ioctl. Code to measure. Disable and read the counter. Ooh, this is pretty cool. You can just do that. ioctl fd perf event ioc reset perf event ioc enable. Then you put in the code. So this is the code we want to measure. Let's say here. Then we do another ioctl on the ft perf event ioc disable. Then we read from the file descriptor. We want to pull this out into a function. So the count is probably U64, right? Yeah. So U64 instruction count or cycle count. Cycle count, size of cycle count. And then we want to printf the CPU cycles. I have no idea if this works. ioctl, of course. Can we trust Gemini for this? Oh. Okay, so let's quickly also set. Oh, we don't want to. We don't want to do that. Wall. See, we wanted to use handles here. Who says that C compilers are not useful? This is probably gonna take a while again, right? Let's compile this with O3 again. Okay. So we have no idea how long this is. And I also don't know which instruction it uses. So this looks like 7 billion, right? 1, 2, 3, 7 billion. So we know that our processor has 3.4, has a clock rate of 3.4. Why is this not possible? This is now I know why. What? Standard. Come on. 3.4 gigahertz. Now 7.48 over 3.4 is 2.2. this could measure the cycle count. Now, let's Linux perf. Let's actually, maybe that's documented. That has to be documented. What instruction they are using here. Perf count hardware CPU cycles on x64. How do we know? How do we know which instruction the kernel uses to measure the cycle count? Okay. RTSC. Yeah, but how do we know this? So what we could also do is use the x86 intrin.h, and it has Intel intrinsics. It has an RDTSC in here, underscore RDTSC. So we could do this. So let's say if Linux perf and if def Linux perf, we do this, and if this is ugly, but okay, and if we could also else start TSC. Oh man, RDTSC copy the current 64-bit value of the, okay. If we use the RDTSC instruction, it does something else, but let's just use the intrinsic. Else, so use64 cycle count is equal to end TSC minus start TSC, and let's say use64 end TSC, yeah, whatever. RDTSC. Now, is that the same kind of number? We see a similar kind of number, right? So it probably just uses RDTSC for the cycle count. Yeah. Yeah, so we have several different ways of doing this, but generally we probably want to use perf because it gives us access to also the performance monitoring counters which go beyond RDTSC, which is just a pseudo cycle count. It may not be the actual cycle count. Yeah. But we can also use RTSC. And we could also use RTSC to time RTSC, or a clock to time RTSC. Yeah, let's just leave it like this for now and continue the next time. Yeah, so we want a very, very robust way of measuring our code to be able to make it more efficient on the machine. Yeah, we can do that with perf. I've never done it before. Yeah, the AI chatbot is gonna help us out, right? I wish